continue our discussion on AC analysis of differential amplifier, and the basic circuit for the differential amplifier was this, containing two transistors. We are taking BJT, and actually finally we will see that this can be done even with the FETs and MOSFETs. And the output is taken normally from the two collectors. This is one collector, this is another collector, C1 and C2. This is RC, this is RC, this is RS, which is normally small. This is the source resistance. This source which supplies the signal, it has an impedance, and that is source resistance. And this is VI1 and this is VI2, I for input impedance, and here is VO, the output. And we were discussing the AC analysis of this basic differential amplifier. For that we said that the purpose of this resistor RE and this DC source VEE is to supply a constant emitter current. Now, so for AC analysis we can replace this arrangement RE and VEE by a constant current source, constant current source. And for AC analysis, as we have discussed this several times, that there are certain rules, and the rules are DC voltage sources have to be grounded and DC current sources have to be opened. So, this source is to be grounded. So, our AC circuit will become this. Q1, Q2, and this we are replacing with a current source. This is DC current source, constant current source, and this supplies the emitter current, and these resistance, source resistance, we are taking negligibly small, so that we neglect them. And here are these, this is VI1, this is VI2, RC, RC, and the output we take from two collectors here, plus minus, this is V0. So, this is the equivalent circuit from the basic operational amplifier circuit, which we are going to use for AC analysis. Now, I said that DC current sources have to be grounded. So, I'm sorry, DC voltage sources have to be grounded, and DC current sources are open for AC. That means they pose a very high resistance, and ideally we take infinity. That means no AC will pass through this path. This we have to remember. Now, from the analysis which we are going to have, these are two sources. So, what we do, we will use superposition theorem. We will take one input source as active, and we will see and ground the other one. We will see what is the contribution in the output. Then we will ground this, and we will activate this second input source, and what is the contribution, and then we will, the superposition theorem says that the net output will be the algebraic sum of these outputs, which will be created by two input sources. From this analysis one very important point we are going to uh, come out, and that is these two inputs of the differential amplifier, they are different in one way, and that distinguishes them. One will be a non-inverting input, the other will be a inverting input, and they are always called like that, inverting input and non-inverting input, because I have said it earlier that differential amplifier is the first stage in the multi-stage amplifier called operational amplifier, which we are going to study just after finishing the differential amplifier. And so, this is very essential to know what is the meaning of inverting input and non-inverting input, and so on. So, we pursue, we continue the analysis, and here this is the circuit, and as I said, the second input source we will ground, and we will see the output of the first one. So, here it is. This is grounded, and here this is active. This is Vi1, and this is grounded, and here this is the DC source. So, open for AC. Now, this is the output which is taken between these two collectors C1 and C2 of transistor Q1 and Q2, and this is V0. This is the situation when one of the two input signals is activated, is active. So, now see the signals that here we take the input signal is sinusoidal, it is like that. Now, several very important points will come during this discussion. What is this? Q1, Q1, this has been said earlier, forms a common emitter CE amplifier, and common emitter amplifier shows the output inverted of the input. So, amplified output will appear at the collector, and here this will be better. Out of this I make a bigger figure. This is open, so we need not to show it. Now, this is the input signal. This will appear here in the inverted form. Why it will be inverted? Because we are feeding to the base with respect to ground, and we are collecting it at the collector, and they are inverted. So, we will get a output here like that. Now, this signal will move here as well, and at the emitter, when we take the output from the emitter, then there is no phase inversion. So, at the emitter the signal will be available like the original. Now, very important point, C1 forms a CE amplifier, but now look here, this signal will propagate from here to this emitter. So, the signal is applied at the emitter, and we are taking it at the collector. This is Q2 CB form. Q2 forms a common base CB amplifier, very important point. This is acting, Q2 is acting as a common base amplifier, and in common base amplifier there is no inversion, but amplification we will just write the expression, this is equal to this. Hence, this signal will be amplified and will appear with this polarity, and hence this will be here. So, what will be the net output because of the first signal source, input signal source Vi1? This is this. This is time and this is VO1 output, net output because of first input. Now, look here, this is the output. You may say how the two will be combined. Now, look here that at this point, if had it been say with respect to ground, this will be the maximum, and now instead of ground level it is more negative. So, this will be, these two will be added. This is like that. We measure the height of this point from this table, then say this is 20 centimeter. If we measure it from the ground, it will be say 1 meter and 20 centimeters. So, that is to be added, and if still from a deeper point we measure this height, that is to be added. So, the same thing, this is added up to that. So, finally, this is the output, and now see here, this output appears for this input. This was input Vi1 with respect to T. So, obviously, this is non-inverting, this is non-inverting, and this input is called non-inverting input, non-inverting, and Q1 is Q1 transistor provides non-inverting input. It is called non-inverting input. Now, we will see the other way. We can find even the amplification actually, and as I said, Q1 forms CE amplifier, Q2 forms CV amplifier, and the amplification will be the output VO1 is A is the gain into Vi1. It is the general expression for the voltage gain, where A is the voltage gain of the amplifier. Now, how much is that? We can, it is very simple because we have done it in the analysis of small signal BJT amplifiers. So, A1, the gain because of CE amplifier, this is RC by RE plus RE prime, where RE is the resistance with the ammeter, where it is simply the I will draw another figure to illustrate this point. here. So, the signal is going to the emitter and hence this will act as Re prime, where Re prime, this Re prime is the dynamic emitter resistance, that is the emitter resistance of the junction, dynamic AC resistance, and here this will come for Q2, but the two transistors are identical, hence they are the same. So, this will be A1 is equal to RC by Re prime plus Re prime. This is from the transistor, one is from Q1, the other is from Q2, and hence this is equal to RC by 2 Re prime, and this is because of CE stage. And similarly, it will be for the voltage gain in CE and CB are identical, and hence this will be A2 for CB amplifier. This is also, this comes out to be 2 Re prime, because for CB the gain is RC by Re prime, but there are two RCs, RC here, RC here. So, they have to be combined, they are in parallel, and hence this will also be RC by 2 Re prime. Therefore, A in this expression, which gives the output A voltage gain due to Q1 plus Q2, this is simply A1 plus A2, and this is RC 2 Re prime plus RC 2 Re prime, and A is equal to RC by Re prime. This is the gain, differential gain, and remember this is that V output, because of first input will be A Vi1, this is equation 1. Similarly, we will get the equation when the second input is second input source is active, we will get another output, and then we will apply the superposition theorem. Always remember one very important point, that we are always in the differential amplifier, when we take output from the two collectors, then always we are taking at C2 with respect to C1. Output at collector C2 with respect to collector C1. This is very important. That is why I said that at the instant when this output was maximum, when we measure with respect to this point, these two will be added. So now, when second source taking second input source active, and here the situation will be this. This is active, this is grounded here, and this is RC, and this is minus plus at that instant when input has maximum, like that, the signal is like that, T versus this is Vi2, this is V02. When this input is active and this is grounded, now the roles will reverse. we are feeding the signal at Q2 at the base, taking it at collector. So, Q2 will be a CE amplifier and inverted output will appear here. So, here the output will be inverted, that means like that. C amplifier, this is the input, just pi phase will appear at the output. So, output will be like that, and this signal goes here, and now Q1 will be CV amplifier. So, without any inversion, amplified signal will appear here. So, at this collector here, at this collector it will be like that. So, when we sum up the two, remember this is C2. So, this with respect to this, therefore, the output VO2 as a function of time, this will be, as I have said, I have told earlier in the first case, this will be like that. When the two, this is measured with respect to this, then this is like that. And this, now compare these two. This is a inverted output here. For this input, this is Vi2 as a function of time, this gives output like this, VO2. So, this is inverted input. One is non-inverted input. Out of the two inputs, this input is non-inverted input, this is inverted input. This we will remember, and they are marked actually, the inverted input with a minus sign in the circuit diagram. It is shown, and in the logic circuit diagram also on the device it is minus, and non-inverted input with a plus sign. So, these are the two inputs. Now, we return back that these are the contributions VO1 and VO2, these are the contributions from individual sources. When the first Vi1 was activated, we got the output here. Now, VO2 is A is the same, because the same thing is being repeated. Q2 forms the C amplifier, Q1 forms the CV amplifier. So, we get the same gain, and this is Vi2, this is equation 2. Now, we apply superposition. So, applying superposition theorem, VO, the when both inputs are active, that means when both signals are present, then the output will be algebraic sum of the two. And they differ in phase by pi, since VO1 and VO2 differ in phase by pi. Therefore, V0 will be equal to AVI1 minus AVI2, or VO is A is common, VI1 VI2. If this difference, if we write the difference Vi1 minus Vi2 as VID, D for difference, D for difference, then V0 is A into VID, or A is V0 by VID. That means this is what earlier we said as a statement. Now mathematically by the AC analysis this is coming true, that in differential amplifier amplifies the difference of the two signals, and so we can write like this, the output where VID is difference in two inputs. So this is very important analysis, and this has brought out several important features of the differential amplifier, that this acts as a differential amplifier plus the two inputs, one is the inverting, the other is the non-inverting input. Then we take another parameter from this AC analysis, and that is input impedance. For every amplifier, input impedance is very important parameter. So, input impedance of differential amplifier. The differential amplifier is always symmetric, So, whether we take the input at the Q1 or we take at the output, it comes out to be the same. And when we measure it here, say at Q1, this is a C amplifier, and for a C amplifier, for CE amplifier, common emitter amplifier, the input impedance for CE amplifier from the analysis, the small signal analysis of bipolar transistors, we have said that this is beta, the current gain, into RE, effective resistance as seen by the emitter, plus RE prime, and this RE is also RE prime, as I take this figure again here. This is from Q2 RE prime. So, this will be seen, and this itself has a resistance RE prime. This IE prime is appearing because of the dynamic emitter resistance of Q1, but this is seeing because the other is also connected, and this current source, constant current source is open. So, this is non-existent for AC. So, this is the path, and so this RE is also RE prime because of transistor Q2, and this result we are not deriving, this we have done. You just look back to the analysis of BJT, small signal amplifier. So, Zi is equal to 2 beta RE prime, because RE is Re prime 2. So, this becomes Re prime 2 Re prime. So, this is the input impedance. In normal small signal amplifiers like having one input like C, B, C, E. So, the C amplifier, this Re prime was 25 ohms, but when we multiply with beta, that comes out to be reasonably high voltage of 1 or 2 kilo ohms. In this case, because this depends Re prime, if you remember, the dynamic emitter resistance of the transistor by definition is 25 millivolts by IE in milliamperes. Then it depends on current, and in differential amplifiers this current is very small, and hence Re prime is very high. Re, if it is 1 kilo ohms, for example, Re is 1 kilo ohms, then this will be, depending on the value of beta, several hundred kilo ohms or even 1000 kilo ohm. So, very high input impedance differential amplifiers have. So, this was about the input impedance. Then the output impedance, output impedance of differential amplifiers. The output impedance, if we look at the diagram, and this is grounded, then between this and ground, what is the impedance which we will be, either we measure here or we measure here, we are going to get RC. I repeat, between the collector and the ground, the impedance which we are going to have, output impedance, will be equal to RC, whether we measure for Q1 or Q2. Therefore, output impedance ZO, this is equal to RC. RC whatever, if it is 500 ohms or 1 kilo ohm, whatever it is, that will be the output impedance. So, the three most important parameters of AC analysis for any amplifier, the gain and the input impedance and output impedance, that completes the AC analysis of the differential amplifier. This was the general analysis, and by general we mean for the differential amplifier when we take the output from the two collectors, that means for balanced output. Differential amplifiers, dual input, balanced output, that is the most widely used configuration of the differential amplifier, and for that we presented the analysis. The DC analysis is same for all other possibilities also. AC will slightly differ, because from whether we are taking output from two collectors or from collector C2 with respect to ground, that will change the gain, and so that part is slightly different. So, having done the analysis for the dual input and balanced output differential amplifier, we can briefly take other configurations. Some are not used actually, but for the sake of argument and for the sake of logic they are there, but others are used. So, what are these and how we can infer the results, because input impedance will be the same whatever is the configuration, whether single ended output or double ended output, input impedance does not depend on that. So, input impedance will not be affected, only output impedance will be affected. Now, the other configurations we take, other configurations of differential amplifiers. The next one we take is this: dual input unbalanced output, that means single ended output. We take output from C2 with respect to ground. This is sometimes used, some special conditions, situations are there where this configuration proves useful and is used. So, this is dual input and unbalanced, that is single ended. Output differential amplifier. This is dual input unbalanced, that is single ended output differential amplifier. What we are saying is this: we are taking output here. This is V out with respect to ground. We are applying two inputs and we are taking, in the previous case, the balanced output, we were taking output at the two collectors C1 and C2. Now, only single ended, unbalanced. So, from collector C2 with respect to ground. In this case, only one point is to be remembered, that let us look at the signal. The signal will be amplified, it will be, amplification factor will be half of the previous case, because here, for example, this signal was amplified here also, and it is amplified here also, and similarly the other one. But here this gain A will be equal to RC by 2 RE prime, because the signals will be amplified. What we are now using is only half the capability of the differential amplifier. I just make this point clear. For example, when both signals were there, the output at the Q1 collector was like this. This was from the collector C1, and the collector of C2, that was like this. Now, if we measure this with respect to ground, this will be the gain. These two are identical as far as the magnitude is concerned, but when this point will be measured, this is double. We explained this, that this will come double. So, in this case, when we are taking output with respect to ground, the gain will be half. Another important point, that because of the symmetry of the differential amplifier, the DC parts were absent because they were equal and they will be cancelled in the output when we take output from two collectors. That means, in the case of balanced output, the DC part was absent. Now this DC part will also be there. So, output will contain DC plus AC signal, DC voltage will also be there. So, if this configuration is to be used, then at some stage we will have to take care, because this will change the DC level of the signal. So, there are circuits which take care of DC level in amplifiers. So, that is to be used. And as I said, input impedance of this amplifier will be the same as in the previous case, because input impedance does not depend how we take the output. Then other configuration is single input balanced output. Single input balanced output differential amplifier. Differential amplifier. This is I draw the figure. Only one input source is there. This is grounded and this is active. And output is taking from two collectors C1 of Q1 and C2 of Q2. So, here this is output. Now, if this signal we take, then we remember that this will appear here as inverted, but here it will appear as like this, and here. So, when we take the balanced output, the voltages input and output, this is in phase with this input. So, this is the voltage time and this is for Vi, this Vi, and output is in phase with it. This is V out. So, we will get the output and input like that, and V0 will be equal to A V1, where A is RC by RE prime, as in the first case we studied. And the last one, which is not used actually, that is single input unbalanced output. Single input unbalanced, that is single ended output differential amplifier. Differential amplifier, and this is the configuration which we are talking. This is the input signal, and output, this is grounded, and output is taken from here V out with respect to ground. This is the single ended unbalanced output. So, here the gain will be half of the first case, plus important feature is that this does not offer any advantage over simple, no advantage over simple C amplifier. But the disadvantage is this makes use of much more components, large number of components as compared to simple C amplifier. So, this is almost never used, there is no advantages in using this, so this is not used. Here gain will be half of the previous case when we take unbalanced. So, A will be R C by half R E prime. So, almost never used. So, these were the different configurations which we had said earlier that 4 possibilities exist, and these are the 4 different differential amplifiers. Now, all through this analysis we have taken BJT differential amplifiers, but instead of a BJT we can use a FET, JFET or MOSFET, and we can form a differential amplifier. For example, a MOSFET differential amplifier. The analysis which we have done, they are with slight modification. For example, gain will depend on not on beta, but you remember that transconductance. So, those terms are to be used, otherwise it is same. So, very briefly I take this here. This is the source resistance, and these are the 2 MOSFETs. This is one input, this is another input, and we connect this is VDD, this is RD drain resistance, and the output can be taken from 2 drains. This is V0. So, these are the 2 MOSFETs T1 and T2, and they can also form a differential amplifier. This is one transistor MOSFET, this is another MOSFET, and it can be shown actually that the source current RS is VSS, this battery, minus VGS by RS, and drain current in 1 is the same as drain current in 2, and this will be half of IS, so IS by 2, and differential gain in this case this will be GM into RD. This also for a MOSFET we have derived this relation. So, this is the voltage gain, and V0 will be AD into VI1 minus VI2 as usual. So, this is the differential amplifier. So, differential amplifiers are common with MOSFETs also when very high impedance, input impedance in megohms are required, or rather still higher, then MOSFETs are used, and this will be the requirement in several instrument fabrication. So, these differential amplifiers are used. Now, we will talk about the constant current source, constant current bias circuits. Constant current bias circuits. In the conventional design, which we have been taken as the basic differential amplifier, this constant current source this resistance Re and this voltage, this forms the constant current. And remember, we have said, we have made a statement several times, Vi1, Vi2. We made a statement, and in the whole AC analysis we had taken this as a constant current source. Now, if we draw the Norton's equivalent of this circuit, then Re, then for that current source, Norton's equivalent will have Re as the source resistance for the current source. For a current source, the source resistance must be very high, ideally infinite. You know, in these this was a voltage source. A voltage source, constant voltage source should have a low resistance, while the current source should have, and we have neglected this Rs at several places, but a current source should have very high resistance. But in this case, Re cannot be very high, because if Re is very high, that will reduce the tail current. Taking very high value of Re, the tail current will be dropped drastically. So, we can't use very high value of Re. So, but a good current source, constant current source should have a higher resistance. So, better circuits, this is replaced by a transistor, and a constant current source can be fabricated by using a transistor, a BJT. So, what will be the circuit? That is this. Because the reverse bias collector has much higher resistance than simple resistance Re. So, this acts as a transistor Q3, this is Q1, Q2, this is Vi1, Vi2, rest is same as we have we have discussed. This circuit is taken RE and the current IE3 flows through it. What we have done? We have replaced the simple arrangement of that resistance RE and this battery, because this does not form a high quality constant current source. So, this we have replaced by a transistor. The transistor collector, which is reverse bias, and that exhibits a much higher impedance as compared to simple RE. So, this acts as a better constant current source, very widely used, because this is essential, this point was essential, that a constant current source is providing a constant current to the differential amplifier, and this can be analyzed in a simple manner. We will be talking about that, and this can further be improved. This resistance R1 can be replaced with two diodes having identical characteristics as this emitter base junction. So, these are the points which we will be discussing, and then we will move further.